Okay, today we will continue by multiple integration, and we will start by double integration, and after that we will continue by integration of double integrals in Cartesian coordinates. So last week we just talk briefly about integration for definite integration for one variable functions, and now we will extend the theory of definite integral to functions in several variables. So we generally deal with functions with 2 or 3 variables, and we start with integration of functions in 2 variables here in this chapter and the second one. And we will recall the motivation here again of definite integral of one variable functions. And if you remind that if f is positive function, then the integral, the definite integral from a to b of fx represents the area of the region determined by y equals fx, the x-axis, and the lines x equals a and x equals b. Similarly, a motivation for double integral is here we will see that it will be the volume of the region under the graph of a positive function, now z equals fxy, lying above the xy plane if it is positively defined, as we write here, positive function. And if we just remind the definite integral for one variable functions, and if we suppose that fx, let me make it okay. So if this is your positively defined function fx on the closed interval ab, as you can see here, the steps that we were doing to find the Riemann sum, to dividing that closed interval AB into n subintervals. And for example, if we take any partition like that, if you suppose A equals x0 and B equals xn, and if you try to have this partition from x0 to xn, so that means you divide the closed interval AB into n subintervals. And if we set the delta xi, which means the length of a xi subinterval, is equal to xi plus y minus xi. And if we choose, for example, if you suppose this is delta x0, the first, the length of the first partition here, and if you pick any value in between those two values, x0 and x1 respectively, and that can be, for example, this point, this one, so that can be this point, for example. And if we suppose that this is xi star, so in any subinterval xi plus 1, and if you remember, we first define the Riemann sum, so which is the area of all, the sum of area of all these rectangles that you can find in many ways, by which depends on the partition that you have here, and also the point that you choose in between all these subintervals. And if you, for all or for any Riemann sum that you try to write, we have seen that in Mathematics 1, if you take the limit when n goes to infinity, which means delta xi goes to 0, that the limit for all these possibilities for Riemann sum approaches the almost the same number. So if you take that limit, that approaches the same number, which we call the definite integral of fx from a to b. So which is actually the area under the graph of fx, which is positively defined here, and above x-axis, and also between the lines x equals b, and also the other line here, which is x equals a. So that area. So this one, this area can be just showed as the definite integral of fx from a to b. So that one, just the definition of definite integral for one variable functions. And now we will extend this idea, the same idea, to definite double integrals. And if we suppose that the function fxy is equal to z, which is continuous, it is a continuous function, and also, sorry, this is that surface. So this is your function now, because you're in three-dimensional space. So that means this is the surface, which is your function fxy, and we suppose that it is continuous function on the domain, which is which contains xi points, where x is in between a and b and y is in between c and d. So this is the domain. That means this is the domain, this one. So this is the domain of your you can say also integration. And now we try to find the volume under fxy and above that domain D. So as you can imagine, it is a volume of a solid, and now here the Riemann sums, for the Riemann sum, if you divide that solid into, let's say, n partition, so the one piece here will be like that. And yes, okay, m and n, yeah, I should say, if you divide the domain D into m times n rectangles, so which means you divide B into n, sorry, A, close interval A to B into n partitions, subintervals, and C to D into M, as you can see here, into M subintervals. And that means you divide the D, the rectangle D, into M times N rectangles. And if you take a sample point here, Pij, from each of these rectangles, so this is again, this makes the possibilities of Riemann sums here, and the volume of the rectangular boxes here, so that means the height of any rectangular box will be Fpij. So the volume of those boxes can be written as sum of Fpij times delta Aij, which is this one. Delta Aij is the area of the base here. And this will be the Riemann sum here, and it will be an approximation of the volume under the graph of fxy and above d, which we actually try to find. So the limit as the number of regular boxes goes to infinity, so the same process as in definite integral for one variable functions, as the length of the size of rectangles goes to 0, is the volume, as we said, of the solid, which is under the graph of fxy and above d. In general, for any function fxy, which is not necessarily positive, for which this exists, that limit of the above sum, we say that fxy is integrable over d, and we call this limit, if that limit exists, as the double integral of the function fxy over the domain d, and also we show it by those two integration signs. So it will be double integral of fxy over the domain d here. So as example, if we take f as a continuous function on the regular region d on xy plane, then f is integrable over d. So if f is continuous, then on that region, then we can directly say that limit exists, limit of Riemann sum exists, which means f is integrable over that domain. And note that if fxy is positive on d, then the double integral of the function fxy over domain d gives, as we said many times, the area under z equals fxy and above d, the domain d. And let's give an example here, a quick example. Here the function fxy is equal to y, so which means this is the plane z equals y. So let me try to sketch it. So this is that one here. This region is the plane z equals y. This is our function, and it is on first octant, it is positively defined, and d is the rectangle here, where x is in between 1 and 4, and y is in between 0 and 5. So if we just try to show the d, this is that, you can just sketch the d sorry, it is from 1, so it is the D. So this is the rectangular region D, and we try to find the double integral of fxy over D. So since fxy is defined as y, you can write it is a double integral of y over that rectangular region D. So if you just sketch, you can see that it is actually the volume of the half rectangular box, because as let's say again, it is the plane z equals y, so that is why it will be the half of the rectangular box here. So this is the sketch of the solid, which represents the volume under z equals y and also above D. And from just the volume of the box, we can find the solution. So which will be, the sides are like that. So here you have 5, I guess, and this side is 3, and the height is 5 also. So this will be 5 times 5 times 3 times 1 over 2, because it will be the half of that rectangular box. Any problem until here? Do you have? Var mı buraya kadar problem arkadaşlar? İki katlı integralle ilgili. Varsa sohbete yazabilirsiniz ya da sorabilirsiniz direkt. So until now we are considering D as a rectangular region. So now here we have a question: what if the domain is not a rectangle? For example, if it is considered at that kind of bounded region. Since D is bounded also, we can put that inside a rectangular box and call it R. And we can extend fxy as 0. So we suppose that it is defined as 0 outside of D. So for outside of D here, so on those areas, we suppose that fxy is 0. So which means the double integral of fxy over D has to be equal to the double integral of fxy on that rectangular area R, where we put our non-rectangular region D, and suppose fxy is defined as 0 outside of D. And in general, we have that theorem. If we let the D region, the bounded and closed region, if we suppose that it is bounded and closed region, whose boundary is a union of finitely many curves, such as circle, triangle, square, if fxy is continuous on that region, then fxy is integrable over D. And if we give the properties of double integral, most of them are very close, or you can say the generalization of properties of definite integral for one variable functions. So here, of course, we let f and g as functions of two variables which are integrable on D. So let's suppose that both are integrable over D. Then we have the followings. If the area D is 0, so that means you don't have the integration area. So the double integral of fxy over D has to be 0 if the area is D, because there will no volume, right? So you cannot express the region which yields the double integration of fxy over that region, 0 region, has to be 0. The second property we have for double integration, the double integral of 1 over d is equal to 1 times from the definition. So that means our function fxy or z equals 1. So which represents z equals 1 plane. So from the definition of double integral that we have seen, this is 1 times the area of D. So that is why the integral of the double integral of 1 over D is actually the area of D. And if fxy is greater or equal to 0 on D, then the double integral of fxy over D represents the volume of the solid, as we had as an example above, under the graph of Z and also above D. For any constant alpha and beta, the double integral, we have this. If you remember, we have the same property for definite integral of one variable, functions of one variable. So here it can be extended for functions of two variables. So if alpha and beta are constants, arbitrary constants, then the double integral of alpha times fxy plus beta times gxy over d is equal to alpha times the double integral of fxy plus beta times the double integral of gxy. So we can, which means we can write the constants before the integration, and also we can let's say divide that double integration from the addition. Okay. And again we have this one for the indefinite integral. So here, if we suppose f and g, we already suppose that they are integrable, and also if fxy is smaller or equal to gxy on the region D, then the double integral fxy over D is smaller or equal to the double integral of gxy over the region D. So which means if f is smaller or equal to g over D, so that one which is a double integral of fxy So if you just sketch as we did above, so if you suppose fxy is positively defined, for example, you can just sketch another function that you call gxy over or above fxy, and you can see that over at the region D, if they have this inequality in between, they have that property, then the volumes, which are represented by double integrals, has to be in that way. So also you can compare the volumes which are represented by those double integrals in that way. And the which one? The sixth property for double integration. Absolute value of double integral of fxy over d is smaller or equal to the double integral of absolute value of fxy over d. Again, this we have seen for definite integral. And let d1, d2, dn be non-overlapping domains, which means they don't intersect, and fxy be continuous on each di, and if we put d be the union of all di's from I equals 1 to n, then f is integrable on d, and the integration, the double integration, can be represented like that: the double integral of f over d1 plus the double integral of f over d2, and until the double integral of dn, f over dn. So if we just try to sketch that overlapping di's, so if we just suppose that this is the region D that you try to integrate, double integrate fxy, and those are di's d1, d2, d3, d4, and d5. And if you say the boundaries, that the boundaries intersect, but since the boundaries of di's, the area of that boundaries is 0, the boundaries of di's may overlap like here, but it will not be a problem. So that means we can compute the double integral over d as we express here. So for example, for this sketch, if you try to find the double integration of fxy over d, it will be equal to the double integral of f over d plus over d1 plus over d2 plus over d3 plus over d4 and plus over d5. And let's give some, I don't know, I'm not, okay, this is the only one example. So the region D here is represented by x squared plus y squared smaller or equal to 1, x is greater or equal to 0, and y is greater or equal to 0. So region D here is this one. So this is actually the quarter of the disk x square plus y square equals 1. So this will be the region D, and we try to find the double integration of square root of 1 minus x square minus y square over D, over that region D. So we know that it is positively defined on the first octant here, if we suppose z as square root of 1 minus x square minus y square, and we know that from the definition of fxy, we know that it is the definition of the unit sphere in the first octant of xy-z plane. So which will be, this will be the volume of the unit sphere. So the double integral will represent the volume of the unit sphere in the first octant of xyz plane. So which will be from 4 over 3 times pi times 1 cube times 1 over 8, we will have pi over 6 square, unit cubes for the double integral of square root of 1 minus x square minus y square over D. Any problem for double integration until here? Var mı arkadaşlar problem buraya kadar? Diğer konuya geçeceğim çünkü. Şimdiye kadar, yani girişte sadece neyi görmüş olduk aslında? Pozitif şekilde tanımlı, değil mi? Bir z eşittir fxy yüzeyinin altında kalan ve bir D region'ının, bölgesinin üstünde kalan bir katı cismin hacmi olarak şu anda sadece iki katlı integralleri hesapladık. Now we will talk about the iteration of double integrals in Cartesian coordinates. So what we will see? We will see the evaluation of double integrals by integration of single definite integrals, and the difficulty of evaluation of those double integrals depend on function as well as the domain itself. So the domain also important. And we start with simple domains, which we will call as simple domains. Those can be in two ways. As you can see from the first sketch, the D can be represented by the set of points which has coordinates xy, and where x is in between a and b and y is in between cx and dx. And the second one again is another simple domain that you can see here. D is that region on xy plane, as you can see. D is the or contains the points with coordinates xy where y is in between c and d, and x is in between ay and by. So if we have those kind of simple domains of integration, then we can express the double integral as iterated integral. So we call them iterated integrals. And if we recall computation of volume of solids by slicing that we had on previous chapter. So if this is our function z equals fxy, and if this is the simple domain that we try to compute the double integration, and the volume, of course that means we try to find the volume of the solid under z equals fxy and above d, that one, and it will be equal to the definite integral of ax, this one, sorry, that one, ax, so the shaded area here actually by red, so this one, ax, from a to b, where ax is the area of section at the point x, which has to be in between a and b, of course. So if you find ax and if you integrate that section from a to b, then also it will give you the volume of the solid that we try to find. And now we will consider a fixed point x and express that ax that we have here. So if you just try to see that ax on zy plane, yz plane, then it will be like that, right? You can sketch it on yz plane like that. You can just think it is project of this section onto yz plane also, so that will be in the figure, like in the figure. So the area ax, of course, will remain same, since the area is in let's say in two-dimensional space, so you can just sketch it in that way. The projection of this section on the yz plane is the region bounded by the, as you can see, y-axis, and the vertical lines, those vertical lines, and also under z equals fxy. So this is ax, this one. And if we try to write ax as a definite integral, then that will be from here, that will be the integral of ax from cx to dx over, of course, y, and combining these integrals we obtain, so to get the volume we obtain the integral of fxy dy from cx to dx, and then the integral of a from a to b, integral of this ax dx from A to B. So this is the volume that we express at first. Then after that we define ax, since the region is simple, defined as a simple domain. Then we try to find the volume of the solid, like that. Okay, so in that way. So this is the expression of double integral as iterated simple integrals, because we define ax as a definite integral, single integral, and after that again we use another single integral here. And we shall, at the end here, we shall just omit the parentheses that we have here, so we can directly find the volume of the solid by that double integration. The important thing here is it is the order, let's say, of dy and dx, of course, important. And also we may extend that iteration for any function, so it is not need to be positive functions. So if you have other type of simple domains, also we can extend that iteration. And also let's see that in that theorem how it will work. Let fxy be a continuous function on the domain D, which is, as you can see, a simple domain. Then the double integral of fxy over D, as we did above, is equal to that double integration. So as you can see, first we integrate with respect to y here, and after that we integrate with respect to x. So that is why the first limit of integration is from c to cx to dx, since you integrated by y with respect to y. Then after that the limit of integration is from a to b, that since you have you integrate here with respect to x. So if gxy is continuous function on D, and now here we have another simple domain, then as you can see here, you have first the limit of integration, which is the, let's say, the boundaries of x, and after that you have, as a limit of integration, you have the boundaries of y. So that is why the other single integral has limit of integration as c, from c to d. And again note that the evaluation of order, or the integration order, is as from the inner, also if you try to compute, it will be from inner integral to the outer integral. So which means you have to compute the inner integral first, and after that you will compute the outer integral. Let's try to see in an example. We will try to find the double integral of 1 minus x plus y. So this is fxy over d, where d is a rectangular region. So this is in both forms. So it is x and y simple domain. So if we integrate it, it is, of course, it will be written from the total order of integration. So first you have to write, since you have dy here, you have to write the limit of integration as the orders of y. So that is why it has to be from 2 to 4. Then after that, since you have dx here, of course you can write in the other way, but then you have to change those simple integrals. So here we have to write after that as a limit of integration the borders of x. So this has to be from -1 to 2. So as I said, since it is x and y simple domain, so it is simple domain of both types, you can directly write this one as, let me see, okay, this is the same, okay, sorry, pardon, diğer tarafı da tam değerinde göstermiş. But if I just say it can be written as, or it can be computed as the double integral in that way. So if you just change the order of integration, the relation order, so that is why first you have to write the borders of x, and after that you have to write the borders of y. But if we just try to compute that double integral in that order, so first with respect to y and after that with respect to x. So as we said, first we have to compute the first single integral here, so which will be, so since you integrated with respect to y, then it will be y minus x times y plus y square over 2. Here again remind that x and y are two independent variables. So here that means x is supposed to be as a constant here. So if you integrate 1 minus x plus y with respect to y, then you will get this. And of course you have to compute that between from 2 to 4, which is the limit of integration, y equals 2 to 4. Then after you compute this, so you got this value, you can compute the integral, again a single integral here with respect to x. So which will be, if you just compute it, this will be 8 times x minus 2x squared over 2 from -1 to 2. So you will get 21. Okay. And if we just swap dx and dy, or we change the order, and we can write, as I said, the double integral, since it is x and y simple domain, in that way. And of course, the computation, after the computation, you can see that it has to be equal to 21 again. Of course, not forget to also adopt the limits of single definite integral. So if you change the order, if you swap dx and dy, that you have to change the limit of the integration. Here's this one and also this one. So as an exercise, you can see the second one. In order dx and dy, the answer will be the same. And another example here, which we will try to find the volume of the solid under the graph of fxy, which is 3x squared times y, and above the region D, which is a region on xy plane bounded by the curves y equals x squared and x equals y over 1 over 3. So first, for the iteration, first we need to express the integration region, so D, the region D. So as you can see, if you just express that y is in between 0 and 1, and x values are in between y squared and y over 1 over 3. So this is the region. This is the region D. So this one is the region D, and we can just express the volume of the solid as double integral of 3x squared y, which is fxy. So if we integrate first with respect to x, then you have to write the boundaries here. This one. So that is why the lower limit will be y squared and the upper limit will be y over 1 over 3. Then you have to write the boundaries of y, which is 0 to 1. So this will be 0 will be the upper limit and 1 will be the lower limit of integration. So first we will compute 3x squared y with respect to x. Integrate 3x squared y with respect to x, so which will be 3 times x cubed over 3 times y, so which will be x cubed times y, and you will compute it between x equals y squared to x equals y over 1 over 3, and you will get y squared minus y over 7. So always remind that you have to find a value in terms of y here, and then you will integrate it with respect to y between 0 and 1. So which will be y cubed over 3 minus y over 8 over 8 from 0 to 1. So which will give you, after computation, 5 over 24. This is the representation of this sketch, just to show the representation of the integration domain here. So if we try to change the order of integration, so if you first integrate with respect to y and x, of course, the boundaries will change. So here you have to write x with boundaries. So x will be from 0 to 1, as you can see from the sketch. Then after that, y has boundaries here. If you write y with boundaries, then here you can write x equals y over 1 over 3 as x cube equals y. So the lower limit will be x cube, and also x equals y square is actually square root of x equals y. You can write it in the first octant like that. So this will be the upper limit of integration with respect to y. So as we already find the volume here as 5 over 24, this one, you can also, by computing, swapping the dx and dy, so first integrating by y and then x, you can also see this has to be 5 over 24 by changing the orders of integration. Okay, as you can see on the example also, if we have to say again, if you change the order of integration, so which means if you swap dx and dy, then we cannot simply swap the limit of integration as we did for simple domains of both variables, so x simple and y simple domains. So that is why you cannot write those double integrals like that. So you cannot just swap the limit of integration as we can see here. So as you can see, we changed the limit of integration here, and as you can see, we change also so the order of integration, then we change also the limit of integration. So that is why we cannot write this in that way. So if of course cx and dx are constant, that means the domain is x and y simple. So in that way you can write it quickly. But if cx and dx are non-constant, as in the previous example, you cannot do the calculation if you change the order of integration in that way. So you have to define the limit of integration again for the change that you have for the order of integration. And of course, you can ask, how can we decide if we have dx, dy? So if you have first x and then y integration, or dy dx. So how can we decide the order of integration? Actually, for those examples like the above, like this one, it is just up to you. So it is a matter of test. But in some examples, some cases, we have forced to use the fixed integration order. So that means you have to use one of those integrations. So you cannot just choose. It is not up to you, but you are forced to use one of them. So let's try to see that in that integration. So we try to integrate fxy, which is equal to e over minus y square. And the region here, as you can see, we can just sketch it from here. The boundaries of y is from y equals x to y equals 1. So it is y equals x to y equals 1. Sorry, y equals x, y equals 1. And the x boundaries is from 0 to 1. So which means x equals 0 to x equals 1. X equals 0 is the y-axis, so this is this one, and the other one is this x equals 1 line. This. So that is why the integration domain is that triangular region, this shaded region. And since we cannot compute the integral of e over minus y square from x equals, y equals x to y equals 1, so from x to 1, we need to change the order of integration. So we have to change it by dx dy. And to do that, we have to first sketch the domain of integration as we had here. So this is the shaded area, so which is a triangle with vertices 0, 0, 0, 1 and 1, 1. 0, 0, 0, 1 and 1, 1. And if we want to evaluate the integration in order to dx dy, we need to write the domain in the form like that. So we have to express the integration domain in that form. So first we observe that y can take any value between 0 and 1, which is the easy one. So this c has to be 0 and y has to be 1, that means. And for the boundaries of x, so which you have to define in that way, we will consider the barriers as our points move to right in the positive x direction. Then after that, we will consider the barriers as our points move to left or negative in the negative x direction. So this can be shown like that. So if we, or we can just first find the lower limit. So if you come, if you come from that direction, then this will be the lower limit, and this will be the upper limit of the integration. So the first one is here, the y-axis, so which is x equals 0 line. So that is why the lower limit here, as you can see, has to be 0 for x, integration with respect to x. Then the upper limit has to be this line, so which is y equals x. So this has to be written as x equals y. So that is why the upper limit of integration with respect to x has to be y. So after this expression of the domain, now we can change the limit of integration. So we can write it as the integral of e over minus y square, so which is fxy. Sorry, here we change the limit of integration from 0 to y, so which we express it here, and after that the integral from 0 to 1. So if after we compute this integral with respect to x, then we will compute y times e over minus y square with respect to the integral of this with respect to y, and we will try to find the value in between 0 and 1, so which will give you the solution of the double integration. And also here in the last step you use the substitution method, where you substitute u as y square, and here we use the method of substitution. And I guess this is the last example. Yes, okay. We will try to express the double integral of f over d as iterated integrals in the order first dy dx, and after that dx dy, where d is the region which is given in that figure, the shaded region here. So first we will try to compute that integral in that order, dy and dy times dx. So the limits of x are, you can directly write the limits of x here. It is from 0, right? It is the y axis, x equals 0, to x equals y. And okay, this is easy to write, but also we have to write the lower limit of, the limit of integration with respect to y, and the lower limit of y coordinates of the points in that region is the x-axis. So that means you come across the negative side of y, so the first one here that you cross will be the lower limit of y coordinates, and the upper limit here, so this will be the upper limit of y coordinates of the points in the x-axis will be the of the points will be the arc here, which is x square plus y square equals 4. But you have to write that arc as y equals square root 4 minus x square, since you need to find the limit of integration with respect to y. So that means you can write the integration of f over that region with the integration of the dy dx like that. The integral of f from y equals 0 to y equals square root of 4 minus x square. Then after that you have to write the limit of integrations integration with respect to x, so which will be from 0 to 1. So this is the integration with the order dx dy. So now we have to find the iterated integral, so we have to compute the same integral with the dx dy in integration order of integration. So now it will be, of course, more complicated than the first one. So let me clean those. So as we had in the previous example, we can first we will decide the y boundaries. So as you can see, we have two parts here, so two areas here that we need to express the boundaries. So the first region, if you suppose the first region as I shaded now, like that, so it is x and y simple domain, so which can be just computed as fxy dx, the integral of fxy dx from 0 to 1, then dy from 0 to square root of 3. Since the region that we shaded here is x and y simple. And after that, okay, I will clean this, we have to define the integral of fxy over that region, the one that I shade now. So for this one, if we use the order of integration dx dy, then first we need to, that means we need to we can directly define the y boundaries. Then after that we need to define the limit of integration with respect to x in that way, but let me show it. So y, let's see the first y boundaries. So y for limit of integration, the lower limit for y will be 3, so this is y equals 3, right, and square root of 3, sorry, and the upper limit has to be y equals 2, so it has to be 2. And for limit of integration with respect to x, the first line is y-axis, so which is as x equals 0. So the lower limit here, let's see again, has to be x equals 0. So that has to be 0. And now we will see the upper limit with respect to x. So this has to be, so if you just come across here, so this has to be that arc, which is square plus y square equals 4. So if you try to write as this as x equals square root of 4 minus y square, then this will be, so let me clean this, so this will be this one, the upper limit of integration with respect to x. So that is why you have to write here for an upper limit with respect to x equals square root of 4 minus y square. Of course, after, if you know fxy, and after those two computations, you can see this one and this has to be both the double integral of fxy over that region D. Arkadaşlar, anlaşılmayan bir şey var mı? Buraya kadar any problem until here. Birazcık uzattım derse. Kaydı durdurayım.